Okay, so hello everyone and welcome to today's edition of our extremal and probabilistic combinatorics webinar. Let me remind you that this webinar is being recorded and we will put the recording on YouTube eventually. So if you have any questions, please either unmute yourself and just pose the question during the talk, or if your audio doesn't work or you rather prefer the chat, then ask it in the chat and then I will read it out to our today's speaker. And as usual, there will be space for questions at the end and some informal discussion as well. Okay, now it's my pleasure to introduce Corrine Yap from Rutgers, and she will be talking about topological Turán problem. So Corrine, please.
Great.
And you have to start screen sharing, I believe.
Yes. Oh, and my slides have been linked in the chat, which is excellent. So let me share my screen. Yeah, thank you so much to the organizers for having me here today. So I'm going to talk about a topological Turán problem. Everything I talk about is joint work that I've done with Jason Long and my graduate advisor, Bhargav Narayanan. As you mentioned, please feel free to unmute yourself at any point to ask any questions. I'll try to sort of start from the very beginning, but let me know if I can clarify anything. And also you can type in the chat. I'll try to keep an eye on it, but it might be easier if you just unmute yourself and ask me. I'll be able to get to questions more efficiently that way. Okay, so let me start. With the background of this problem that I'm talking about. I think most of us should be familiar with the sort of basic Turán problem, or the more traditional setup, which is this. So given a graph H, how many edges can an n-vertex graph have while containing no isomorphic copy of H? And a lot of work has been done on this problem. We know a lot of answers. There are some answers that we still don't know. But this was really, the foundational problem of this whole field of extremal combinatorics. So of course it's been generalized in many natural ways. And I'm going to propose to you two different ways to generalize this problem. The first, which you might have already thought of, is what if we replace a graph with our uniform hypergraph, or an R graph? So hopefully we're familiar with the term our uniform hypergraph, but just in case you aren't, we're thinking of a collection of subsets of vertices, where now the subsets of vertices can be any size, not just two. And for our uniform, I'm specifying that every subset or hyperedge has size exactly R. So we can ask the exact same question, but about hypergraphs. And again, some stuff is known about this problem, some stuff is still unknown. I want to take this one step further and ask this additional question: what if we also replace the word isomorphic with homeomorphic? And now it might seem a little less natural of a question to ask, mainly because I haven't told you what it means for hypergraphs to be homeomorphic. So there are no topological spaces being involved or running around here, so it's unclear what my notion of homeomorphism is referring to. If you think back to the last time you thought about topology, maybe you remember that we define homeomorphisms between topological spaces. Technically they're continuous maps with continuous inverses, but really it's a relationship that allows us to say when two topological spaces are the same in some sense, or they share some certain invariance. So to have this question make sense, I need to give you a little bit of the topological setup and the sort of viewpoint that I'm tackling this question from. So let me give you the topological point of view that we'll be taking today. And so maybe you're familiar with these terms, and maybe you haven't seen them before. Either way is fine. Hold on, my pencil has disconnected somehow, so I can't draw. 1 second. Okay, I have to stop sharing my slides so I can reconnect my writing pencil. So give me 1 second. Let me fix this. Okay. Okay, it is back. So let me reshare. Okay, sorry about that. So let me introduce a few definitions in case you're not familiar with them. So we'll be talking about simplicial complexes. And really, we're going to be considering sort of abstract simplicial complexes. So I just define those as a vertex set and a family of subsets of that vertex set. So similar to a hypergraph. But this time I'm requiring that they are down close, that is closed under taking subsets. So if I have a set in my simplicial complex, then I require that every subset of that set is also in my simplicial complex. And these sets of vertices that are in my simplicial complex, I will call those simplices or faces. And maximal faces will be called facets. And mainly we'll be thinking about simplicial complexes where the maximal faces all have the same size. And my notion of size will be the dimension, which is just the number of vertices in my simplex minus 1. And the dimension of my simplicial complex is the maximum dimension of its faces. So in case this is all new to you, to sort of absorb all these definitions, it might be easier just to look at an example and think about that. So for instance, what if I have my set of vertices is, some set A, B, C, D, E, and I can sort of abstractly define a simplicial complex as just, some collection of subsets. So maybe I have ABC, and then AB, BC, ABC. So that's all of its subsets of ABC are in there. And then maybe I have, I don't know, BD, CD, DE, B, D. Okay, so I could write it as this, but sort of a more intuitive representation is to actually draw it. So I can represent this simplicial complex like this, where now I have to think about labeling these vertices the way that I actually wrote them. So I think this is correct. And I'm going to shade in this triangular face. So sort of everything that I've drawn in the picture represents a simplex. So I've shaded in the triangular face ABC to represent that that triple of vertices ABC is one of my simplices, whereas I haven't shaded in BCD because I am not including BCD as a simplex. And if I look at the facets, so there are many different facets here. For instance, ABC is a facet, and BD is also a facet. And if I calculate these dimensions, the dimension of any triangular face will be 2. The dimension of any edge will be 1. And we can see that the dimension of the simplicial complex overall is going to be 2. So this is sort of just a toy example, but are there any questions about this definition or this notion? Okay. So then how are we going to relate this to our original setup? We're dealing with the Turán problem for hypergraphs. Well, we can think of these hypergraphs that we mentioned before as, you know, these sort of geometric or topological structures, mainly simplicial complexes. So let's suppose R equals 3. And how do I go between a simplicial complex and a hypergraph? For any hyper edge in my H, I can simply take the sort of down closure of that set. So graphically, I'm just sort of filling in this triangle. So this would be in S. And similarly, if I look at my simplicial complex S, and I look at all of the facets, I can just take every facet to be an edge in my hypergraph. And so in particular, we can define homeomorphisms between hypergraphs by really thinking of them as homeomorphisms between these simplicial complexes. Because as it turns out, these simplicial complexes are topological spaces. And so the notion of homeomorphism makes sense there. In particular, this triangle is homeomorphic to just the disk, so S1. And if we think about in surfaces, two-dimensional objects, then we can take any triangulation of the sphere, for instance, and we can say that's homeomorphic to the sphere itself, the two-sphere. And in general, a triangulation of a surface is going to be homeomorphic to the surface. And really, those are the main types of homeomorphisms that we'll be thinking about today. So you don't need to think about weird things that might happen with continuous maps. You can just think about triangulations and the idea of sort of subdividing simplicial complexes. For instance, the notion of subdividing a graph, those are really all the homeomorphisms that we need to deal with when it comes to just normal old graphs that we're used to. So this is how we're going to impose our sort of topological structure on the problem. And now I can actually say precisely what the question we want to answer is. And this was something that was first posed by Nati Linial. And he introduced this in what he called his high-dimensional combinatorics program. And the question was this: given a K-complex S, and by K-complex I mean K-dimensional simplicial complex, how many facets can an n-vertex K-complex have while containing no homeomorphic copy of S? And for facets, I assume they are all K-dimensional. I don't think you have to assume that, but it sort of makes the things that we're dealing with a little bit easier. So what is already known? What has already been done on this problem? So, I just realized that if I go forward a slide, that this will disappear. So I guess I will copy it and paste it. So what's already known? We cite this in our paper as folklore, but you can also read it from results by Erdős on these so-called degenerate Turán problems. What's known is for a K-complex S, there is some exponent, lambda of S, which is greater than 0, such that every K-complex on n to the K plus 1 minus lambda of S facets contains a homeomorph of S. And so just a note, why are we comparing to n to the K plus 1? Right, this is because the maximum number of K-dimensional facets, S, or let's say that there can be on n vertices is n choose K plus 1. Right, so we're sort of comparing it to the maximum number of facets we could possibly have. And we're saying that we're discounted by this lambda of S factor, and that is enough to guarantee a homeomorph of S. So that's what's known, that for each simplicial complex, we can find this exponent. But you might think that this exponent, well, it can rely heavily on the structure of the S that we're looking for. For instance, if S is something very simple or very sparse, for instance, maybe it's just two edges glued together, then it might be a lot easier to find that than a really complicated, dense structure. So a question to ask kind of after this is, can we find some sort of universal exponent, lambda sub k, that works for any simplicial complex of k dimensions, that is a lower bound to all of these lambda of s's? And so that was actually the question that we were focused on trying to answer in the paper that I'm talking about today. There was some work done previously on this problem, on answering this question. For instance, Mader has a famous result from 1967 that says lambda of 1 is equal to 1. His result was not worded in this way, that he was looking for this universal exponent lambda 1, but it regards finding subdivisions of graphs, because for one dimensions, we're just dealing with what we call graphs. And so what he said is that a linear number of edges is enough to guarantee a subdivision of any fixed graph. And so that's known for sure. Then Brown, Erdős, and Schoch have shown that lambda of S is 1/2 when we take S to be the two-sphere. And more work has been done recently on specifically two-dimensional simplicial complexes. In particular, the work that sort of jump-started what I'll be talking about today was this paper by my two co-authors, Jason Long and Bhargav Narayanan, along with Peter Kivash and Alex Scott, that found the existence of this universal exponent for two dimensions, and in particular found a lower bound of 1/5. But they conjecture that this is not tight, or that this is not the best that we can do. And in fact, last, I guess, October or November, Kupovsky, Polyansky, Toma, and Zakharov showed that lambda of S is 1/2 if S is not only the two-sphere, but a triangulation of any closed orientable surface. And so this sort of provides some evidence that maybe the correct answer is 1/2. It seems like a reasonable conjecture to make. And let me just mention as an aside that Andrei Kupovsky gave a talk at this seminar about this paper called The Extremal Numbers of Surfaces, and there is still a video of it on YouTube, so I would recommend you go watch it. It's a very nice talk, and I think the methods that are used in this paper are very different from what I'll talk about today. So if you're interested in this problem, but maybe looking for more different methods to think about, you should go watch that talk. Because one sort of important commonality between these two works is that both arguments really relied on the geometry of the space. They relied on the fact that we were dealing with two complexes, or equivalently 3 uniform hypergraphs. And in particular, the extremal number of surfaces paper really used, things that we know about surfaces, about two manifolds, like the classification of orientable and non-orientable surfaces. So when we try to generalize to 3 complexes, or in general K complexes, it's unclear if we are able to do that with these methods, because there are things that we know about surfaces that we just don't know about higher dimensional manifolds. And so it is, in some sense, you think that you might have to start just totally from scratch when you're trying to deal with general K complexes. But as it turns out, there was a way to, in some sense, generalize what was used in this first paper to come up with our main result for today, which is that this universal exponent lambda k does exist for all natural numbers k, for all dimensions. And we found a lower bound of k to the negative 2k squared. So this is the main theorem that I'll talk about today. But first, a couple of observations. This is far from tight. For instance, it gives you lambda 2 is bigger than 1 over 2 to the 8th, which is quite far from the previous bound that was found of 1/5. So we're not claiming that we can do sort of better than than what's already been done, but the sort of novelty of the proof is that it's purely combinatorial. It doesn't have to deal with specific things that we know about 3 uniform graphs or about 2-dimensional spaces. And in particular, we use 2 main combinatorial or probabilistic tools. The first is that we introduce this notion of a trace-bounded hypergraph. And the second is that we use a version of dependent random choice, which was sort of inspired by the methods that were used in the first paper by Kivash, Long, Narayanan, and Scott. So that's the main theorem. Before I go on, I want to make sure and answer any questions if there are any, because after this, I'm going to start talking about the proof methods and specifically these 2 tools, and sort of get a little bit more into the nitty-gritty of how we prove this result. So before I go on, are there any questions about the setup, any of the history of the problem, or just the statement of the theorem?
So maybe I just overlooked, but is there any, for a general K, is there any non-trivial upper bound? So could it be that lambda K equals 1/2 always?
Oh yeah, so it could be, it's possible that lambda K, yeah, I guess it is possible. I hadn't thought about it. So we conjecture that lambda 2 is equal to 1/2, but we don't have any, or at least I don't have any ideas of yet on proving that. There is something in the chat. Yeah, Bhargav said, so it's probably not 1/2 in all dimensions, and I'll mention this at the very end. But the fact that lambda of S is 1/2 for the 2-sphere S is sort of, I don't know, and that the correct answer might be 1/2 makes you guess maybe that lambda of SK for the K-sphere might be the correct answer, but we also don't know what lambda of the K-sphere is. So, but you know, it's not clear that that would be 1/2. And yeah, Bhargav mentioned in the chat that random constructions show lambda K must decay as K goes to infinity. Yeah, so I haven't specifically thought about that, but I would trust what he may be remembering.
Thanks.
Yeah. Any other questions? Go back to this slide. Okay. All right, so let me get into the techniques that went into this proof. So I'll start with the first and tell you what a trace-bounded hypergraph is. So the trace of an R graph on a subset of vertices is, you can also think about it as a sort of projection of the edges on that specific subset of vertices. We just take every edge in our graph and we intersect it with that particular set. And in particular, we'll be dealing with mainly with R-partite graphs. So I'll let my notation be x1 through xr for my parts of G. And I'll abbreviate the trace of G onto the first I parts as just the ith trace, or trace sub I. And then this new sort of property that we introduced of D trace bounded is this. So G, as I define it above, an R-partite, R uniform graph, we call that D trace bounded if for each trace, so for the ith trace, I can bound the degrees by D for every vertex in specifically the ith part. So let me illustrate this with an example. So suppose that I have my G here, and let me just draw some blobs. And let's say R equals 4. And I'm going to label it this way which is probably backwards from the way that you would intuitively think of labeling it. When I was writing my talk, I was trying to come up with ways to sort of justify that this was a good way to label. Really, it's just because I've been drawing all the pictures in this way the entire time I've worked on this problem, so I cannot change it. So I apologize. But what does it mean to be d-trace bounded? Well, let's start with I equals 4. Then the fourth trace of G is just G itself, right? We're taking the trace of G, so sort of the intersection of every edges with V1 through V4, which is all of G. So being d-trace bounded means that if I look at all of the 4 edges containing this, I'm sorry, I'm also terrible at drawing, that this degree is bounded by D. So degree of V is less than D for V in V4. So those are all bounded. But now what if I look at I equals 3? Now I'm looking at the intersections of all the edges with just V1 through V3. And I'm saying that the degrees of everything in V3 are bounded by D in the trace. What that means is that I can think of sort of the forward degrees, so all these 3 edges, that degree is less than D. But in the general graph, my degree might not be bounded. I could have some, large, in terms of D, some arbitrarily large number of edges going sort of backwards from V3. But I can think of the forward direction as being bounded by D. And then if I look at the second trace, so that would be V1 and V2, again, I can have my forward degrees be less than D, or I need my forward degrees to be less than D, but my backward degrees can be unbounded. And then my last trace that I'm dealing with, the first trace is just the vertices in V1, and that imposes no restrictions because the degrees are all 0 there. So I drew this picture because I think about it as sort of forward and backward degrees. So I'll write that, and if you don't like that way of thinking about it, you can ignore this. So you can think of the forward degrees or the rightward degrees are bounded. The backward degrees are not necessarily bounded. Okay. Yeah. Okay. It's good to have Bhargav here because he can answer the questions in the chat. Yeah. So a question was asked: is this somewhat analogous to degeneracy? And Bhargav responded somewhat, but not quite. Yeah. So I'm not as familiar with the degenerate problem as Bhargav is, but I will mention a little bit about that. I think actually maybe on the next slide. But before I go on, are there questions about this definition? Okay. Oh, something in the chat. Okay. So with this notion, we can actually state what the main combinatorial result that we proved is, which is this, that we can actually find an exponent that alpha RD, so it is only in terms of the uniformity R, and then the degree of the d-trace boundedness D, such that if I take any d-trace bounded R-partite R graph, then I can guarantee now just an isomorphic copy of it in a graph with at least n to the R, discounted by, alpha RD edges. And so this is now just kind of the first generalization of the Turán problem that I mentioned way back on that first slide. Now we're just dealing with embedding, finding copies of hypergraphs in larger hypergraphs. And if you know anything about this problem, then this might mean something to you. If not, then ignore what I'm about to say. But by itself, this theorem gives a universal lower bound for what are called Turán exponents on degenerate trace-bounded hypergraphs. So this generalizes a result by Conlon, Fox, and Sudakov, where they have a similar statement, but they require more of their graphs. So this might be what was being mentioned in the chat, that in this Conlon, Fox, Sudakov result, they require that all parts, or I'll just write it here, all degrees are bounded in, let's say, x2 through xr. So in all but one of the parts, the degrees are bounded by D, which is a stronger thing to require than just saying that we're D trace bounded. We're not saying that the degrees have to be bounded in the general graph. Okay, so that was just an aside. But this is the main combinatorial result that we have, which is just, can be taken on its own as a sort of Turán result. But let me explain how this gets you to theorem 1, which was about embedding or about finding copies of homeomorphs of simplicial complexes. So let's say that I have, and let's just take r equals 3 again, because that's the easiest sort of non-trivial example to draw. So let's say in my S, I have some number of these two-dimensional simplices. And I want to find a homeomorph of S. So what I can do is I can construct a specific homeomorph. And I'm going to draw it. Okay, I'm going to draw it a little bit bigger. It's still homeomorphic, even though I've drawn it bigger. And what I'm going to do is introduce some new vertices and then sort of subdivide my facets. And the way I'm going to do that is I will introduce a new vertex for each subset of this triangular face. So I'll have one new vertex for the entire set of 3 vertices and one new vertex for each edge. And then I will just sort of subdivide it appropriately. I could write out, in notation what precisely I mean by that, but I think maybe the picture is more illuminating. And you can imagine that you would be able to do this in higher dimensions. So I do this for every edge. So for every facet. Sorry, not for every edge, for every facet. And so it's easy to see that this is, that if you do this for every facet, then this will give you a homeomorphic copy of S, a homeomorph of S. And then I want to relate this to a D trace bounded R-partite R graph, so 3-partite 3 graph in this case. And based on the way that I colored the vertices, you could probably guess what graph I'm going to, or how it's going to be 3-partite. I'll have my pink vertices and my green vertices and the original black vertices. And I will label it in this way, V3, V2, and V1. So the hypergraph that I'll get out of this will be 3-partite. Why is it trace bounded? Well, if I look at the degrees in V3, those have to be just bounded degrees. And you can see that for any of these pink vertices that I introduce, they will only ever be adjacent to or included in the facets that arise from this particular facet that I started with. So in particular, this vertex will only ever be included in these 6 new facets. So actually, my vertices in V3 will have degree 6. And then if I look at V2, it's possible that the degrees in V2 are unbounded, for instance, in terms of D at least, or in terms of, well, I haven't told you what D is, but D will be 6 in this case. My degrees in V2 could be very large. How about that? Because what if I have something weird happening in my simplicial complex? Maybe I have, for instance, in this facet that I've drawn, maybe I have a bunch of other triangular faces sort of coming off of this edge. You know, I'm trying to draw them sort of like as flaps. Then this green vertex could be adjacent to many of these pink vertices. But it's only ever going to be adjacent to these two particular black vertices in V1. So my green vertices will have degree 2 in this case. Even though I could have some large number of vertices in V3 that they're adjacent to. And then my vertices in V1 don't have any restrictions. And that's also good because this example shows us that there might not be a good way to bound the vertices in V1. And in general, my D is going to be k plus 1 factorial, I believe. And we'll be subdividing each k facet into k plus 1 factorial new facets. So this is how I can get a D trace bounded R-partite R graph from my simplicial complex. And so what do I do? Well, if I can show that theorem 2 holds, then I am able to find a copy of this particular hypergraph in my original graph with at least some number of edges. And when I view both as simplicial complexes, that means I get a copy of this simplicial complex, which in turn is a homeomorph of my original simplicial complex that I wanted to find. So it's enough to show that I can find this D trace bounded graph in my general graph G. Okay. So are there any questions about how we got from theorem 2 to theorem 1? Okay. So now let's talk about proving just this result. So for the rest of the time, we're going to forget about any homeomorphs and topology. We're just going to be dealing with this main combinatorial result. And there are techniques that have been used in the past that, sort of arise when thinking about this type of theorem, mainly dependent random choice. And so this was something that I mentioned was used in the previous work that we were trying to generalize. And so we'll use that to our advantage in this construction, because what we want to do is embed our H, our D trace bounded H, into G. So let me start by describing, if you're not familiar with it, what the sort of general idea of dependent random choice is. And then I'll explain what we actually used, the notions that we actually used for our specific problem. So my notation will be that my graph G that has at least n to the r minus alpha r d edges, that is on parts x1 through xr. And the graph that I want to embed is on parts y1 through yr. And we can assume that we can assume everything's R-partite. In particular, G is R-partite because if we take a G that's not R-partite, we can use a sort of averaging or expected value argument to sort of pass to an R-partite subgraph. So we can just start off by assuming that G is R-partite. And what we want to do is we want to embed H into G. And ideally, we'd like to do this one part at a time. And so we have to come up with a way to do this sort of consistently or nicely. So let me draw some pictures. So let's say I have my copy of H. And I have my copy of G. And these are YR minus 1, Y2, and Y1. And this is XR minus 1, X2, and X1. And let's say for the moment that I have found a way to embed Y1 into X1. So let's say that I found some embedding phi. And what I want to do is then embed y2 into x2. And now how can I do that? Well, let's say that there is some vertex v in y2. What would be good candidates for the image of v in G? Well, we can look at the neighbors of v in y1. So I'll call this n1 of v. And certainly v in its embedding has to be included in an edge with those neighbors. So if we look at phi of n1 of v, then the sort of candidates for v are the common neighbors of that image. So the candidates for phi of v are the common neighbors of phi of n1 of v. So ideally, we'd like to be able to just pick one of those common neighbors, and maybe we can just do it greedily. Just go down the list of common neighbors and pick the first one that hasn't been used yet. But what's an issue that could arise? It could be that by the time we reach v, maybe we've already embedded some previous vertices from y2. It could be that we've actually already embedded all of those into the common neighbors of phi of this neighborhood. And so the issue would be that we have no options left for v. So an issue is what if all these common neighbors have already been used? So that's sort of the main issue that arises here. And the technique of dependent random choice sort of allows us to say, okay, in X1, there's actually a nice subset or a good subset that we can map Y1 to where we won't run into this problem. So dependent random choice says there exists a good subset of X1. Where when we look at the sort of n1 of v, so all of those over all the v in y2, and we look at their common neighborhoods, those are large enough that we avoid this sort of problem. And so that's the main advantage of dependent random choice. And where the name comes from is the fact that in order to find this subset, or in order to show that the subset exists, we use a randomness argument. We sort of find a random subset of X2, and we look at its neighbors in X1, and we say, okay, this random neighborhood has these properties. So in showing that this good subset exists, that's where the randomness comes in. Okay, so that's kind of the main idea of dependent random choice. But for our particular problem, things get a little bit more complicated because we don't want to do this. We don't want to use this idea just once. We want to be able to embed H into G, the parts of H, iteratively into G. So we want to first apply this to Y2 and then to Y3 and so on until we've embedded YR. So the details get a little bit more complicated. And I'm going to be sort of very vague and wave my hands in this next part because there are sort of a lot of technical details and a lot of calculations that I don't really want to get into, but rather I want to give you the sort of broad strokes of this construction. So what are the potential obstacles that we run into when we're embedding our specific H, our D-trace bounded R-partite H? So one is, I already mentioned that we have these sort of small common neighborhoods that prevent us from embedding the next part. The second problem that's sort of unique to this is that we may not have enough extension possibilities. Now, what do I mean by that? Let me draw another picture. And I've defined the link here, but let me draw the picture first and I'll come back to the definition. So you can ignore the definition for now. Suppose that now I'm just going to go back to R equals 3. Suppose that I have H, and maybe I've found this structure in my H, where V, so this is Y3, Y2, Y1, where the edges containing V look exactly like this. I have these 4 edges that involve V, and I want to be able to find this structure in my G when I embed it. So I have G. And let's say that I've found sort of the right half of this subgraph, that I've been able to embed Y1 and Y2 in a nice way so that I get this. Then how can I extend this to V? Well, ideally, there would be a lot of sort of common neighbors of this subgraph. So there would be a lot of ways, there would be a lot of candidates for V itself. So there would be a lot of these vertices that this subgraph could then extend to create this structure. But again, we run into the same problem, right? What if all of my candidates for V are sort of taken by the time that I reach V to embed? So we have a similar problem so this is for 2, 2, 1. And so we want to sort of avoid this. We want to say that the number of ways that we can extend a subgraph is enough that we won't run out of options when we reach V. And so here's where I define let me be a little bit more precise about this. Let's define something called the link of a vertex. And you can think about it as sort of the trace of, I guess, the edges containing V on its neighbors. So it's essentially, it's the R-1 graph where you take every edge with V in it and you just delete V from that edge and you keep the remaining part of the edge. So for instance, here, the link of V, of this specific V, is going to be this graph, this 2 graph. And so what we want to say is that we want that if J appears as a link of a vertex in H, then any copy of J in G is the link of many vertices in G, or is in the link. So this is what I mean by we want there to be enough extension possibilities, that if we have any subgraph that could come up in H like this, that when we find a copy of it in G, no matter which copy it is, then we can extend it in a lot of different ways. And so that we don't run out of these candidates for V. So then when we want to make this more precise, we define this sort of notion of a bad copy. And this is where our D-trace bounded hypothesis comes into play. Because what are all of the subgraphs of H that could arise as the link of some vertex? So let me go back to the previous thing. What could possibly have been the link of this vertex, right? I picked a specific structure that was this link, but it turns out that this link, it can't be just anything because we are D-trace bounded. The fact that we're D-trace bounded means that the link has to have at most D edges in it, right? Because this vertex has degree bounded by D. And if I added another part, then I could say the same thing about, like for instance, if I added another part here, I could say the same thing about the vertices in Y2 as well. Its link in the trace also has to have at most D edges in it. So it turns out that the things that we are concerned with being bad or not, the things that we are concerned about not extending enough, those all live in what we call HTD, the collection of T graphs that have at most D edges. And so for each J, each possible thing that could arise as a link, we want to identify the bad copies of J in G. And these bad copies are the ones with small neighborhoods or not in enough links in G. And this is the part where, there are technical things. I could say some numbers and do some calculations, but I won't. And so what do we do with this? Well, we essentially want to say that we can embed things in a nice way that we avoid all of the bad copies. And once we avoid all the bad copies, then that sort of allows us to embed H part by part very nicely. And so that's what this lemma is for. So let me copy that. This lemma, which is sort of the main, driving force in the proof, is sort of vaguely written as this. If we have a T-partite T-graph with many edges and few bad copies of each possible graph that could arise in a link, then we can find a T-1 partite T-1 graph in its trace with many edges and few bad copies. And we can quantify what we mean by many edges and few bad copies. So what this does is this allows us to iteratively embed H. So we sort of apply this lemma, R or R-1 times, until we have identified a good subset to start with. Sort of identify a good subset of X1 where we can embed Y1 and avoid these bad copies. And then we go to Y2 and embed Y2 into X2. And again, we continue to avoid the bad copies. And we keep doing this until we've come up with our good embedding of H. And so that's the main idea that arises in the proof. And in the end, we end up with our copy of H as we wanted in the beginning. All right, are there any questions about the main ideas or anything that I've discussed so far? Okay. So that's sort of the end of the proof sketch here. So let me just say what questions we are left with. So this was mentioned earlier, but I'll say it again. What are the optimal values for lambda k? We know that our lambda 2 bound was far from correct, but there's some evidence that might point to lambda 2 being 1/2. We conjecture that our bounds for lambda k for higher dimensions are also not correct or not tight or optimal. So it'd be interesting to find what those optimal values are. In particular, looking at lambda for the K-sphere would be interesting because that might give us a hint as to what might be the correct value. And for higher dimensions, it's not known what this value is. And lastly, what are some optimal values for this alpha RD? So you can consider the problem of the D-trace bounded hypergraphs just on its own. And it would also be interesting to find out if we can improve on this alpha RD. We had a lower bound of something that was like 5 RD to the 1 minus R. And we think that you can do better with that. Okay, so I think I will end there. And of course, you're free to ask me any questions, but let me end by saying thank you.
Thank you, Corrine. And could I ask people to unmute themselves and give Corrine a round of applause? And please, if you have any questions, just unmute or stay unmuted and go ahead with your question. So maybe I have one concerning the proof, or so if I understand correctly, this result of mother for graphs, in order to get with linearly many edges to get a copy of your favorite graph, you need to consider long subdivisions. You can't do just with one subdivisions or two subdivisions. So whereas to me, it seems that you are doing sort of one subdivisions here, right? So the question would be, if you would consider 2 and 3 subdivisions, then maybe could you get a better exponent, or could you do something with your method?
So you're saying that with the particular, so when I drew this picture of, I was saying we're considering this, particular homeomorph. You're asking if I consider, sort of a different structure here. Is that what you're asking?
Well, right. I mean, it's like you decided that out of all these homeomorphs, you just want to search for a copy of this one.
Right.
And you could go down with your exponent by, 2 to the minus k square or whatever it was. So if you consider a different homeomorph, which would be, maybe repeating this subdivision procedure twice, then my question would be whether you could get a bit better exponent.
Yeah, so maybe well, maybe Bhargav can say something about if he's thought about this, but I'll say that in the first paper, that was exactly what happened in the original Kivash, Long, Narayanan, and Scott paper. There was a way that you could subdivide. Actually, you could for two-dimensional simplicial complexes, you could have gone with this subdivision, but in that paper they chose to go with a different homeomorph that had more subdivisions in it to do exactly what you said, to get a better exponent. So here we sort of chose this because we use the notion of D-trace boundedness. And so we sort of generalized in that direction. But I don't know, so I don't know if choosing a different one would give us better exponents, but maybe Bhargav can say something.
I'll add just one small comment. Can everyone hear me? Am I unmuted?
Yeah.
So I believe that, for example, if you look at spheres in 2 dimensions, so you're trying to find, you're looking at this Brown-Erdős-Schuss result that says the exponent is 1/2. One can show that you can only get 1/2 if you do, as you say, look for things of unbounded size. If you're looking for a bounded size sphere, the exponent is strictly bigger than 1/2, as you can work out from some sort of random construction, I think. So certainly, to get the correct answer, one needs to start looking at unbounded size subdivisions. The problem, of course, in higher dimensions is that there are so many of them, it's not at all clear which ones you should go looking for. With graphs, it's sort of clear that really the only things you can do is sort of subdivide the edges into long parts. But even with 3 graphs, it's not at all clear if there's a canonical candidate for how to find big subdivisions, which is partly why this conjecture that lambda2 is 1/2 is still quite open, I'd say.
Yeah, thank you. Thank you. And then another question, which is maybe much less specific, is whether there wouldn't be any counterparts or any problems which would be sort of much less combinatorial, right? So like, if you tell a topologist that you are counting edges and you get a certain result, then I don't know, will they be that excited? Isn't there for them some more natural notion of density?
That is an interesting question. Since I'm not a topologist, I don't think I could answer that. Even if I thought I could answer it, I don't think I would be the appropriate person to answer it. Yeah, that's a really good question. I don't know if there are any topologists in the room who thought, this talk seems very unnatural. I would rather ask this question. So if you do, speak up.
Yeah, I don't know what other good sort of candidates are for the size of a complex, I suppose.
Yeah.
You could look at, I don't know, various sort of invariants. And I don't know enough algebraic topology to even start speculating.
Yeah.
So I think Gil had some interesting questions based on maybe computing homology or something like that. But I don't remember it off the top of my head, but I'm happy to. I think it's on his blog somewhere, and he was talking about this himself.
Yeah, thanks. So let me switch off recording now. For those of you, of course, anyone is free to stay connected. For those of you who want to disconnect now, please mind that in 1 week we will have Marcus Michelin talking about so no graphs, but random polynomials. But that's you know. So I think some very, very nice recent developments there. Okay. Yeah. So thanks for the talk, Corrine. That was
yeah. Thank you.
That was really, really nice.